Hello students, my name is Abdullah Momin from KMES English Medium High School and Junior College, and this is your 6th lecture of chapter Sound from class 11th Physics. And in this video we are going to learn about speed of mechanical wave. So speed of mechanical wave depends upon the elastic property and density of the medium. The same medium can support both transverse and longitudinal wave which have different speeds. So if a wave is traveling in a medium, the medium should have the property of elasticity and density, and both wave can have different speeds in the same medium. Now the speed of a wave is determined by the restoring force produced in a medium when it is disturbed. So if a wave is traveling in a rope and when it is disturbed, the wave will set into the rope, and the speed of that wave can be determined by the restoring force. And the speed also depends on inertial properties like mass density of the medium. The wave produced on a string, a transverse wave, in this case, the restoring force is provided by the tension in the string. So the medium should have, or the speed of a wave is determined by the inertial properties and restoring force. And the restoring force in this case, when a wave is set into the rope, the restoring force is provided by the tension in the string, which tends to bring back the particles to its equilibrium position. So here the speed of a wave is determined by restoring force as well as inertial properties like mass density, and here the restoring force is provided by the tension in case of transverse wave. Now the inertial properties means linear mass density, which is denoted by small m, can be determined from the mass of the string, that is capital M, and its length, as linear density is capital M by L. Now if we want to calculate the linear density, we should know the mass of the string. Suppose the mass of the string is 2 gram and the length of the string is 4 meter. 4 meter length, if this string has a 4 meter length and its mass is 2 grams, so the linear density is mass upon length, that is 2 by 4, which can be written as 1 by 2 or half. So we will say that the linear density of the string is 0.5 kg per meter. Means if we will take the string of 1 meter, then its mass will be 0.5 kg. And the formula for speed of transverse wave on a string is given by. This is the formula of speed, which is denoted by V, and it can be written as root T by M, where T is the tension in the string and M is the linear density. But the important point here is that the speed of transverse wave depends only on the properties of a string, that is T and M. It does not depend upon the wavelength or frequency. Since we know that velocity of a wave is n lambda, but here the velocity of transverse wave is depends upon the property of medium only, that is T and M. Now, speed of longitudinal wave. In case of a longitudinal wave, the particle of the medium oscillates forward and backward. So we know that longitudinal wave consists of compression and rarefaction. Compression means the region at which particles are crowded. This is the particle of the medium. This is the particle, and these particles are moving forward and backward along the direction of propagation, in this direction only. This causes compression and rarefaction, which travels in the medium as the medium possesses elastic property. So this medium possesses elastic property, and when longitudinal wave travels in the medium alternately divided into compression and rarefaction. Now the speed of sound, which is the example of longitudinal wave, means the speed of longitudinal wave in liquid and solids is higher than that of in gases. So when we compare the speed of sound in different medium like liquid, solid and gases, so in case of liquid and solid, the speed of sound is more as compared to the gases, means sound travels with much larger speed in liquid and solids as compared to gases. Now the speed of sound as a longitudinal wave in an ideal gas equation is given by Newton's formula, which we are going to discuss in our next video. But here one table is given to you in which the speed of sound is mentioned in different mediums. So here this table consists of two columns. First column is medium, gaseous medium, liquid medium and solid medium, and second column is about speed, which is calculated in meter per second. So gaseous medium like air at 0 degree temperature, the speed is 331. But when we will increase the temperature 20 degree, the speed of sound in air when the temperature of the air is 20 degrees Celsius, the speed is 343. Means temperature increases, speed also increases. Now the speed of helium or the speed of sound in helium, the medium is helium gas, the speed is 965 meter per second. While in case of hydrogen, the speed of sound is 1284. Now this is the speed of sound in liquid, and now this is the speed of sound in solid liquids. This is the speed of sound in gaseous medium, and this is the speed of sound in liquid medium. Like water, if a sound is traveling in a water and the temperature of the water is 0 degree, its speed is 1402. And if the same sound is traveling in a water of temperature 20 degrees Celsius, its speed is 1482, and the speed of sound in seawater is 1522. Now the speed of sound in solid, vulcanized rubber. So in case of vulcanized rubber, the speed is 54 meter per second, while in copper, the speed of sound is 3560. The speed of sound in steel is 5941. The speed of sound in granite is 6000 meter per second, while in aluminium it is 6420. So by looking at this table, we can say that the speed of sound in liquid and solid is much larger than the speed of sound in gases. So that's it, student. Thank you. Thank you very much for watching this video. I will catch you next time.